All right, hello everyone. I've been requested to go over isomers in a video, so here it is. Okay, so basically isomers are going to be any two molecules that have the same overall formula, but have some kind of difference in their structural formula, so in the way that you would draw them out. So you can see kind of the start of that, iso meaning different, and mer kind of meaning pieces. So different arrangement, some kind of different arrangement of atoms, even though we have the same atoms that are in there. So if you look at some examples of those, we've basically got it broken down into structural isomers and stereoisomers. So structural isomers are when we've got different bonds in the molecule. So we've got three main types here. We can have the chain being in some kind of different shape. So here we've got butane and 2-methylpropane. Both have the same formula. They're both 4 carbons and 10 hydrogens, but we've got different shapes there. We can have a functional group in a different location. So here we have hydroxyl group being on the second carbon. Here it's on the first carbon. So one would be butan 1-ol, one would be butan 2-ol. And we can have a different functional group being present altogether. So here we've got an ester and a carboxylic acid. They have the same molecular formula, but they have different structural formulae. So therefore we'd say that they're isomers of each other. We've got stereoisomers as well. There's two main types that we're learning about this year. We've got cis-trans isomerism. So we have a cis isomer here, where there's two main groups and they're on the same side and of this double bond. And we've got the trans one here. So trans means opposite, going to be on opposite sides of this double bond. We've also got optical isomers, which is where we have at least one stereocenter. So basically some point in a molecule which is connected to 4 different groups. So here this carbon atom is connected to a methyl, an ethyl, a hydroxyl, and an H. So therefore it's a stereocenter, and there's 2 different ways that we can arrange the atoms around that. So you see that this one here, we've got the hydrogen coming out of the page and we've got the hydroxyl going into the page. If we have it the other way around, there's no way that you can physically kind of twist those bonds around to go from one to the other. You would have to break the bonds and reorganize them to get into a different spot. So stereoisomers have the same bonds. Both of these have a hydrogen and a hydroxyl bond into a carbon, but it's just that they're in a different arrangement compared to the methyl and the ethyl. All right, so let's really quickly go through some practice questions. Now, to do with isomers, there's not really an isomer question. There's a couple of things that might show up on the multiple choice that I'll show you, but most of these most things to do with isomers are things that show up in terms of other questions. The majority of the times it's shown up in the past is in terms of spectroscopy questions. So you can go and have a look at my spectroscopy section if you want for that. And where basically they'll say that there are 3 different isomers, tell which one that you have using spectroscopy. And then you'd use the NMR or whatever, and you'd figure out what the structure is. So the isomer here is mostly just meaning there's a few different structures it could be. You're going to have to figure out which one it is. Often in the VCAR exams, they give you the molecular formula, and it's just up to you to figure out the structural formula. So let's have a go at a few of the ones that mention isomers. So we've got, draw the structural formula for a tertiary alcohol. There's an isomer of hexane 3-ol. So hexane 3-ol, 1, 2, 3, 4, 5, 6. Hexane 3-ol is going to look like this. All right, now we need a tertiary alcohol. So a tertiary alcohol is one that where the OH is connected to a carbon that's connected to 3 other carbons. So we've got 4 carbons here. Now, note that it does say a tertiary alcohol. There's probably a few different ways that we could do this. So at this point, I've got 4 carbons. I can add 2 more carbons. Now, any arrangement of hydrogens, any arrangement of carbons here, the number of hydrogens would be the same. So as long as this bit's tertiary, I could have had the hydroxyl here or here or here. Sorry, I could have had the hydroxyl and the other methyl group here, and it would also be a correct answer. So if I draw all the hydrogens on, And note that it says structural formula, which means that we're going to need to add all our hydrogens on. If it said skeletal, we wouldn't even need to write the C's here. So if we counted up all the hydrogens here, it should have the same amount as on here. So this would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So both of them have 6 carbons, 14 hydrogens, and 1 oxygen. So therefore they're isomers of each other. And we can get a nice big tick for 1 mark there. How many structural isomers have the molecular formula of this? Okay, so a few different things we can think of here. First thing I'm going to check is whether I have a double bond. Now I've got, remember that for if it's an alkene, you've got basically twice as many hydrogens as carbons, or hydrogens and other stuff. So here I've got 8 things bonded to 3 carbons, and the only way I can get that is if there are no double bonds. Next, we can have a look at the carbon chain. Is there any way to rearrange this carbon chain into a different shape? No, there's no way you can rearrange 3 carbons into something else. If we have 4, then we can get these different combinations, but while we're working on 3 carbons, we can't do that. So we don't have to worry about the chain having any isomers there. And so we've got Br and we've got Cl as the main points, which they can be different. So if I'm just going to start with the Br, how many places can I put the Br in? Well, I can put the Br here, or I can put the Br up here. Should just say bromine. So I can put the bromine on the left, or I can put it in the middle. If I put it on the right, that would just be the same as putting it on the left, because you could just spin it around 180 degrees. So from here, I can think about which places I can put the chlorine on. So I could put the chlorine on here. I could put the chlorine on the middle, or I could put the chlorine on the opposite end. So there's 3 isomers there. On here, I can put the chlorine on the end, or I can put the chlorine on the same place as the bromine. Again, if I put it on the right here, you could just rotate it and it'll be the same thing. So we found 5 different isomers for this one here. This is mostly basically a deduction process. Problem solving how many different ways you can combine these 2 things together. Which of the following compounds can exist as cis and trans isomers? So to have cis and trans isomers, we need to have a double bond. And we need to have 2 different groups on each side. On each side of the double bond. If we have 2 of the same group on the same side of the double bond, then it doesn't really matter what the other side is, because you could always just rotate it 180 degrees to get the other one. So for example, here, if we look at A, we've got ethene, but there's no cis-trans isomer because there's no way we can, if we swap these 2 hydrogens around, then it'll just be the same thing. So see how it's on both sides, it's symmetrical across here, so it can't be a cis-trans isomer. Next, we've got propene. So we've got this. Now again, on this end, it's asymmetrical. We've got a carbon, we've got a methyl group on this end, but a hydrogen over here, so that's okay. On this other side, it's symmetrical though. So regardless of which way, so if we, for example, put the methyl group on the other side here, it would just be the same thing, right? Because you could just rotate it 180 degrees that way, and you would get back the original molecule. So this one's out of the question. Oops. Get some space. Okay. Here we go. So we'll have CH3, C double bond to C, and then we've got CH3. Okay, now we're asymmetric on both sides of the double bond. We could have them be on the same side here, but I had to make a choice. I could also have put the CH on the other side. It would be something different. So this one is going to have a cis-trans isomer. This one here doesn't actually have a double bond either. It's a fatty acid. We'll talk more about those in the food section of the course, but basically we can see if they're all CH2s, there would be a CH if there was going to be a double bond in there. So this is just basically an alkane with a carboxylic acid on the end. So therefore there's no double bond. All right, there are a number of structural isomers for the molecular formula. So we have a molecular formula. 3 of these are propanal, propanone, and prop-2-ene-1-ol. So we've got propanal here. Write the semi-structural formula for the ketone isomer propanone. Again, you see that it's not a lot of these questions aren't really to do with isomers themselves. It's more just that isomers happen to be in there. So we can write the semi-structural formula going from left to right across here. Propanone, ketone. Remember, an aldehyde is the CO double bond O on the end. C double bond O in the middle is a ketone. Write the semi-structural formula. There's one mark there. Draw the structural formula for the isomer prop-2-ene-1-ol. Okay, so it's going to have, so I'll draw my 3-carbon chain. There's a 1-ol there, and 2-ene means there's a double bond between the second and third carbon. So it's going to look like that. And I'll finish off by adding my hydrogens onto here. Here you go. So again, it's not really an isomer question. It's more just you happen to be drawing things that happen to be isomers. The molecule with the structural formula below reacts with hydrogen bromide. How many different structural isomers can we get here? Well, basically we're getting HBr, and this is going to be an addition reaction. So the H can go on one side and the bromine on the other, in which case we'll get H, CH3, CH3, and then the other side will go to bromine, CH3. Or we can do it the other way around and have the bromine go on this side and the H go on that side, in which case we'll get a bromine here and we'll get a H going on the other side. So we get 2 different isomers there. We would get one if both sides were the same, but this side has 2 methyls and this side only has 1 methyl, so it does differ depending on whether the the bromine goes on the left or the right. And that's about it. So there's not, again, I keep saying it, there's not a whole lot you need to be worried about in terms of isomers. So most of them, it's just a matter of when the word isomer comes up, you know that it means that it has the same molecular formula. They even normally address it during the questions. The only other thing that I haven't covered here would be you need to be able to identify a stereocenter, but I did talk about that briefly. Basically, if you can find a carbon that has 4 different things going out of it, then it's got a stereocenter, and therefore it's an optical isomer. We'll also just talk more about this in the food section, because the food section, optical isomers, they don't matter in a lot of ways in kind of conventional chemistry, but when we go into biochemistry, optical isomers are a huge deal and make a massive difference in terms of food and medicine and things like that. So we'll talk about that a lot more when we get there. Again, let me know if you've got any questions, and other than that, I will see you later.